Okay. Hi, everybody. Thanks for coming, especially as there's a conflict with physics topic right now. So, welcome. Today we have Professor Gil Holder, who is the Brandon Monica Fortier Endowed Chair of Theoretical Astrophysics at the University of Illinois, Urbana-Champaign. His work has covered early universe physics and CMB, gravitational lensing, and black holes. Today he's going to be giving us a seminar about CMB experiments as wide-field astrophysics surveys. So Gil was a professor at McGill and spent some time at CITA. So let's give him a warm CITA welcome.
Well, it's always a pleasure to be here at CITA. I think the first time I visited was probably going on 30 years ago. Every few years I come through. It's always nice to be back. Mainly I'm going to talk about CMB experiments, wide field astrophysics surveys. This is mainly if you don't care about the CMB, should you still be paying attention to all of your CMB colleagues? And the answer I hope you will come out with is yes, that there's all sorts of astrophysics mysteries and things to do, even if you don't care about FNL. All right, so here's an example. So there's new catalogs of interesting objects. So I'll give you some examples of that. Something that's fairly new is that we've noticed that the millimeter sky is actually varying with time, which I think lots of other astronomers realized the sky was time variable. We're kind of late to the game here. So we can make maps of weak gravitational lensing. That's what my main job is these days. And then things like mapping out the large-scale structure density fields. So, things that normal astronomers do that don't necessarily care about FNL. All right, so just as a disclosure, let's not forget that there's still lots to do here. So I'm not saying that CMB as CMB is done, and then I'm going to move on and say that there's other stuff to do. So here's where things were a couple of years ago in the CMB. So here's the CMB power spectrum in T, in polarization, in B. And I think what you can notice from this is that the temperature power spectrum is extremely well measured. And by this, I would say there actually is very little left to do in the CMB using the temperature fluctuations. You see in EE, so in polarization in the E mode, you actually see the error bars are starting to blow up out here at L3000. And the resolution of the ground-based experiments is up to something like here. Which is to say that as the experiments get better from the ground, the noise will go down and these error bars will get tinier and tinier and tinier. And you can see there's lots more peaks out here to measure, which is to say there's lots of signal to measure out here on small scales where there isn't any information in the temperature. So there's lots there. And then you see that in terms of the B modes, we're really just getting started on measuring the peaks. So don't say everyone's quitting CMB, there's nothing left to do. There's tons to do. That's just not what I'm going to talk about today. It's just the primary CMB.
Well, this is the power spectrum.
That's in the power spectrum.
And then there are other surfaces.
Yeah, right. There is, it depends on, yes, there is the bispectrum and the higher order stuff. That's true. But even then, it still remains to be true the temperature is pretty played out. Just because we are basically sample variance limited out to here, and then from here on out, it's just foregrains. So there are a wealth of experiments that are coming. So here we were for the SNOMAS process, 2022. So advanced act was finishing up, SPT3G. This is what I'm going to mainly talk about today. So we're going. We've basically been extended out to here. BICEP is down here. So Simon's Observatory, there's a lot of people here that are interested in, involved in that. And then in the 2030s, we're moving towards this thing, CMBS4. Let's put those in perspective here. So this is a cartoon, but I would say it's accurate to, factor of, 20%, 30%, something like that. This is just taking most of the CMB experiments I could think of and putting them on a plot so you can compare them all. So, WMAP is up there. So what this is the sensitivity. This is the RMS noise per pixel. So, and the unit that we measure in the CMB is micro-K arc minute, and that says if you have a 1 arc minute pixel, how many micro-K would be in there. And then if you had a 2 arc minute pixel, your noise goes down, right? So you double the size, your noise goes down by a factor of 2. So that's why the unit is micro-K arc minute, because you then divide by the number of arc minutes squared in your beam, and that'll tell you what your RMS is.
The question is, why is the azimuthal component of power spectrum getting averaged out? Is it not astrophysically relevant?
So the assumption is that the azimuthal component just looks a lot like, so the assumption is that everything is isotropic and that it doesn't matter which direction you look. So what we're assuming is that the universe doesn't have preferred angles, so you can just do an average over 2 pi in this direction and everything will work out. So this axis has been cut off. Okay, but what it is resolution. Yes, this must be the angular resolution in arc minutes. So you want a high floating medium controls. Good. All right. This axis down here is resolution in arc minutes. So this is bicep Keck is here, and bicep Keck array, which is ongoing, is here. Now, this stuff is not so good for what I'm going to talk about today. Everything I'm talking about is what we can do at high resolution. And here you see a lot of SVT and ACT, and these are different generations of the experiments. And then SO is what's being built, it's right there. S4 is here. Now, so what do we get out of this? Is that, so over the years, different iterations of SVT and ACT have traded off having sort of similar sensitivity and various different ways of surveying the sky, but one's at the South Pole, one's in Chile. We've had a sort of friendly, unfriendly competition depending on who you talk to. And so where we are right now with SVT is we're down here, 2 micro-K arc minute. So I'll convert that to astronomical units in a second. The next generation, so SO is going, then S4 is going to do something like 70% of the sky at slightly deeper. And then there'll be a little tiny patch of S4, which will be ultra deep. And so what these lines are here is constant point source sensitivity. So that's saying if you have a point source, what's the RMS temperature intensity in that pixel? And so what you see is that, so what we're seeing with SVT 3G right now are the same kind of sources if they're unresolved as what S4 will see. We just have a much smaller footprint on the sky. Okay, so that's the landscape. Is that over time, experiments are getting more and more sensitive by just adding more and more detectors. And then there's basically 2 classes, whether you're just going for the low L or the searching for the tensor to scalars out here, or high L power spectrum and astrophysics. So that's where we are. Okay, so we have questions about this? This is sort of the landscape. All right. So a lot of what I'm going to talk about is the South Pole Telescope, and we've been doing this since 2008. So it's just been different generations of detectors. The current generation is this one, SVT3G. It's about 15,000 detectors at 3 different frequencies, and it's with linear polarization, IQ and G. So it's a 10-meter telescope at the South Pole. So what does it mean? Well, here's what Planck would look like at 143 gigahertz, and here's SVT. And so you can see we're really starting to see these dots. So what are these dots? We call them point sources. Other people would call them galaxies. And then there's something right here. You see a hole in the sky. So we call it so this is a galaxy cluster. That's the Synyadz-Aldovich effect. You just see by eye, there's a galaxy cluster right there. This is likely a nearby big galaxy cluster with a radio source at the center. So you can see that, for one, you see much finer scale resolution on the CMB, and that says you get high L power spectrum resonance. But then now you're obviously starting to do some astrophysics because you're seeing some sources that are not primordial. All right.
Quickly, we're about to say this. How much resampling the sky is
So, right. So with SPT, the main field is this 1500 degree patch. So that's mainly what we do is 1500 square degrees. SO, which is coming online, I think, within a year or something like that? I don't know. Is basically going to be doing something like half the sky. So eventually we'll have maps. So the SO maps aren't quite as deep as ours, but they'll be doing maps like that over something like this much of the sky. And we're doing this 1500
I
square
was
degrees.
asking because of transit.
What was that?
I was asking because of transit.
Uh-huh.
You know, I mean, how many times do you look at the same patches?
So with SPT, we look at the same patch typically roughly once a day. Yeah, so I'm actually going to talk about transients, and you'll see some light curves. So I don't know whether once a day is fast or slow for you. It's annoyingly slow when you see a transient, because you're like, oh, I wish I saw more of that. But all right, now, so there's some technical details I don't care about. I'll skip over those. Let's convert these into astrophysical units. So SPT 3G, we're right here. Oh, CMBS4 is this one right here. So you see this is the same point source flux as what 3G has. So in something like a week of observation with S4, so S4 is going to do 70% of the sky looking like the map that I just showed you, instead of that 1500 square degrees. So the real science bands are in here, and you see that the RMS in millijanskis is, it's just below a millijansky. So if you're an astronomer and you think in millijanskis, CMB experiments are measuring things just below a millijansky, as in the coad. And if you were looking for transients, it would be at a few millijanskys. So if you're wondering for your favorite source jiggling around, we're thinking about noise at the level of 5 millijanskys, something like that, is when you can start to be measuring things with SH.
Well, how long an integration does it take to reach that sensitivity?
So with SPT, we spend about 10 minutes going across a source as we scan back and forth. Sorry, that's not right. It'll spend about 20 minutes in the field of view, and then we'll move on, and we might come back to it that day, or we might not. But it's typically about 20 minutes of integration to get to something like a 5 millijansky RMS. And then the question is, how often do we come back to it? And that's a scan shred. It's saying, how do you fill the whole sky? And so that's something we can control. All right. So here you see all these dots. And you would say, oh, okay, I see all these dots. There's a galaxy cluster right there. Probably Chris can't see it, but lots of other people can. There's all these dots. And you would think, okay, well, there's not that many dots there. Surely all those dots are well understood. Well, so here is, this is confusing, stay with me, nu F nu versus wavelength. You wonder why it's not versus nu for one. So it's nu F nu versus wavelength. And here are the limits for CMBS4. These are and then these are just a few different SEDs you can imagine for some astrophysical sources. So this is a BL lac, I think. So it's some blazar that's been redshifted to Z of 1. So you take some nearby red blazar, redshift it to redshift 1, you plot its SED, and make it just barely detectable. Make it be one of these things that's one of the faint dots in here, maybe a little fainter than this one right here, kind of like that one. Something barely detectable in the SPT map. And then say, how bright would it be in everything that we've used? And what you see is that nothing until LSST would be able to see that object. So lots of those dots that we see are actually not visible in any of the IR or optical bands. They would be possibly there in some deep radio surveys. So that's a blazar. So then you say, okay, what about a high redshift dusty star forming galaxy? Well, a high redshift dusty star forming galaxy would be completely invisible in the radio and completely invisible even to LSST just because it's dusty. So there's lots of sources that actually are effectively visible only either with deep targeted observations. If you had some sub-millimeter telescope and you drilled down, you'd be able to see it, but you'd have to know where you're looking. So there's lots of sources that actually most surveys are not going to pick up that you need a millimeter wave telescope to find. So then another one that's kind of a fun example is if you had some planet at 700 AU that was some number of Neptune masses, LSST will see it, and you'd see it in a CMB survey, but you're not going to see it in pretty much anything else. So it's possible there are planets hiding in the outer solar system that have yet to be discovered that we will find in CMB surveys. All right, so here's some examples of those. So here are the radio sources. So these are these blazars. So some of them are optically invisible, only visible in the radar. In the radio, so there's only a cartoon of them. But one of these dusty sources, one of these dusty star-forming galaxies. So it's not exactly this one, but it's one like this that we discovered with SPT. Is actually this source right here, SPT 0418, which had a lot of JWST early imaging. So that was one of the early JWST sources, was various visions of this ring. And with JWST, you can see these. So, but that's the kind of stuff that you could do. So you could find new interesting sources that you will only discover with a CMB survey. So now, where we are, so these points right here are the first generation SPT camera. So with SPT 3G, we're now going to be down to about here. So all these sources down here, so this green line are dusty star-forming galaxies that are unlensed. The ones we detected were almost all lensed. The only reason they were bright enough for us to detect them was because they were lensed, and that's why this thing is this perfect ring. So what we're going to be into now are this unlensed population, which some will argue is more interesting and some will argue is less interesting. It depends on what you're interested in. If you're interested in lensing, it's less interesting. But we'll also be getting into these populations. So it's an interesting place to find new sources. So there are dark spots in those maps are just SC selected galaxies. So these are galaxy clusters. There's a couple famous ones, the Phoenix, El Gordo. So this was the motivation for SPT was actually to find galaxy clusters. We found a bunch of galaxy clusters. So this is mass versus redshift. And what you see is that we're finding galaxy clusters that are just a few 10 to the 14 solar masses up to redshift, well, almost 2. So 1.5. So you can see we're pushing down in mass. And so the thing is, you find galaxy clusters out here, and you're finding the things that abundance matching wise are actually very similar to the things down here, like the Coma cluster. So you're finding the clusters that had the same number density as Coma, but you're finding them as they were at redshift 1.5, which people are pretty excited about to study galaxy clusters. All right, now, that's pretty confusing. So the whole point of this plot was basically to compare the right-hand axis, which is Jansky's, to the left-hand axis, which is limiting magnitude. And I want you to realize that a 10 to the minus 3, which is millijansky's, that's kind of this sensitivity that we're talking about, corresponds to a magnitude of about 16. So for people who speak magnitudes, current the state-of-the-art CMB surveys are like doing a 16th magnitude survey, which isn't really very deep, right? So compared to these optical surveys, 16th magnitude is not very deep. However, you got to start somewhere. This is the first generation of these big sky surveys in the millimeter. So it's not like we're doing Palomar here or something. Like it's still a real survey. It's just, we could do a lot better. So if you talk to people that say they would like to build a much bigger millimeter wave telescope, you should listen to them, because there's, if you could actually push that down deeper, then you're actually doing an interesting survey. All right, so here's what we're talking about is the cadence. So here's a movie that's actually on Vimeo. It's taken by the Bicep Winter Rover, and this is just SPT scanning the sky. And so obviously it's been sped up. And if this is all we're doing, is we're just scanning back and forth over and over and over again. We scan back and forth. Every scan across is about about 10 seconds. So it's about 10 seconds across, 10 seconds back, just back and forth, back and forth. We go back and forth and then up a little bit, back and forth and up. And we'll just tile some number of square degrees in a 2-hour observation. And then we take a break and then we start again. And this goes on for years. So the instantaneous field of view is something that's in some number of square degrees. So SO is going to be like 8 degrees. We're sampling at 100 hertz. So if you can think of a way for FRBs to be millimeter bright, we could actually have a chance of seeing them in the time. We have multiple detectors on a single pixel on the sky. So in principle, if you can think of a way to have very fast surveys, those could be pulled out.
Well, what's your, then you're limiting what?
Oh, then it'd be quite bright. So I think it works out that the sensitivity is right around a Jansky millisecond or something.
Okay.
That's roughly speaking, maybe
Square
two.
the FRB range.
Yeah, if it's flat.
But that's flat spectrum.
Yeah, this is at 90, 150, 220 gigahertz.
Yeah.
So you would need it to be flat in noon, which I think is what most things don't do, but it would,
A lot of them narrow that. So.
yeah, it would be worth looking. And especially there are people here, so certainly if you had CHIME, there's overlap in the sky between CHIME and ACT, and with SO. So in principle, you could plan observations that you could look for coincidences. So we're at the South Pole, so it's harder for us to do. So we could do stuff with the Australians, but it would be a lot harder than SO plus ACT plus CHIME, where you have people who are in both collaborations. So I'm assuming there's someone here doing that, or at McGill maybe. Surely somebody's doing that analysis.
So I guess as a practical question, do you feel that there's enough noise in the system that you would want the radio coincidence to claim a convincing detection? Or would you guys be bold enough to actually saw a blip and publish it?
Well, I think the reason you want the radio coincidence is that you wouldn't need to have such a high false detection rate, right? Because if you're at 100 hertz, then you have, so we're talking about, we usually fold our stuff down to observations that are 2 hours long. But at 100 hertz, you just have so many pixels to check. You would have to set like a 12 sigma cut or something before you're to be not overwhelmed by Gaussian noise. And so, but if you have the radio coincidence, then you can actually look in that pixel, and even a 3 sigma detection would be interesting. So
In that perspective, lower frequency is again most sensitive.
yeah, those would help.
Thermal noise is less.
Well, yeah, and it's also just the case that in the millimeter, we're only going to have about 3 pixels. So at any one time, we have 3 detectors on a given spot in the sky, and if all 3 of them go off at once, and that says, oh, we found something, but it's only 3. It'd be nice to, sometimes you flip a coin and get 3 heads. So we'll see. But just to give you a sense of the data, so here's like 3G data on some source. I should have written down which one it was, but there's 2019 data on it. Here's 2020 data on it. And this is just the flux density in millijanskis at 3 different frequencies. And you just see these things wobble around. And every one of these is one of our observations. And so typically it's roughly 1 a day. We just have these long baselines, so there's gaps at various points, and then there's gaps between here because we took time off when the sun comes through. But you just see these things wander around. They go up and down. So there's a paper by John Hood, now postdoc in Chicago, where you can say, okay, well, let's look at the Fermi data and the optical data. I don't know why that says X-ray, it's not X-ray, it's SVT. So this is the SVT data, and then just looking to see if these things are going up and down together. And so it's a fishing expedition, you see what you can see. So one thing that I'm thinking about doing is maybe looking in the time series to see if I can see echoes, and then you can possibly find gravitational lenses. So if there are unresolved gravitational lenses, you should get multiple images that are all just on top of each other but separated by some time delay. So if you saw some big step, and then you saw another little step in here that came before it or after it, that would tell you that these two are possibly gravitational lines. So this is one thing you can do with the data. So if you're interested in what AGM do, you can do that. So here's a fun thing, which, so we can actually measure asteroids. So here is some asteroid, you look in the JPL horizons and you say, oh, here's an asteroid, so here's where it was on various days, where it is in our patch. It kind of came into our patch, I guess it came in this way, it came in here, slid along. So you just basically make a coad stacked on there, and then you pull out the image and you see, oh, okay, there it is right there, and measure its flux. So we get that at 3 different frequencies, and you can use that to actually look at the thermal emission from these asteroids. And so Paul Chichura, who's cut off from the bottom, he actually went through and he developed a thermal model where you integrate down into the center and you look at the conductivity of this thing as it rotates. And so that thermal emission depends on exactly what the geometry is, the albedo, like how much light's coming in, the composition of the asteroid, thermal conductivity. So that's 4, there's going to be thousands of these. We're going to have thermal measurements of these things. So what I can't figure out is if they're good for anything. So we can't figure out what the killer app is, because the problem is that we're going to see thousands, but that means that we're still going to be measuring things that are like 30 kilometers across. So as far as we can tell, we can't save the Earth this way. That anything that we can see should already be known about, unless it's got some kind of unless it's been painted entirely black. So if there's something that is actively trying to kill us, like it's hiding from us, then we can save the world.
Have you spoken to Avi Loeb?
What was that?
Have you spoken to Avi Loeb?
I have spoken to Avi Loeb, yeah, that's exactly right. Now, here's actually a really fun thing. Here is another moving object that we stacked on. And so this was done by Alan Foster, who's now a postdoc at Princeton working on SO, and he's writing a paper about aspects of this. And we have 3 frequencies, 90, 150, 220, and we measure this thing. And what this is the COBE satellite. We have actually detected, moving across the sky, the COBE satellite with a ground-based CMB experiment. And I was trying to convince him to write an April Fool's paper on this, talking about how we could calibrate off of COBE. And that'd be really funny, but it's like, papers take a long time. Yeah, so in fact, he is writing a paper about about not measuring satellites, basically saying how much do you have to worry about satellites going forward as a contaminant for these ground-based experiments. So we have all the same problems as real astronomers now. Now we have to worry about satellites, asteroids, all these things that other astronomers need to worry about. All right. Okay. Now, so here's another transient. So this right here is a 3-color 9150 220 coad of our data. So you can't see it on here. There are some small-scale fluctuations in the background, and then some dots. That's the coad over a whole season of data. Here's one particular day in 2020, and what you see is that there's something here that wasn't there in the coad, and that was not there the next day. So something in our map just went and turned on and went away. And you can see just by eye that this thing turned on, and it was one of the brightest things in our field. So a genuinely super bright object just turned on. So see, so this is that one, it's another one. But here's, every day's observation, bouncing around, and then one day it went up, went back down again, and then went even higher, went up to 500 millijanskis, that's the peak. And then what was this? Well, it turns out this is a star. So this is Z-end, it's a star. So here's our flux for that day, centered on a WISE image, and you can see we are definitely centered on a star. So it turns out there's just a huge number of stars, well, not huge, but there's 66 different stars in our patch that have periodically just been going off. And they go off in an observation and be one of the brightest things on our entire survey for that day, or whatever fraction of the time was there, and then would turn off again, and we were just completely missing them because we weren't paying any attention. We were just taking the time stream, every day's map, we'd bring it in, put it on the pile, bring it in, put it on the pile, bring it in, put it on the pile. And one of those days, there'd be a brand new source there, we just blindly put it on the pile, not even think about it. And then one day, someone said, hey, why don't we check? And so now we have all these stars going off. And some of them, we can actually see them go off pretty quickly. This is CC Airy. Oh, sorry, this is the end. You see on the time, this is minutes down here. On the time scale of it's about 10 minutes for this one, when up and came down. There's lots of other ones that are just on for the entire, we'll see them for maybe 10 minutes before, a couple hours before, they'll be off, and they'll be on while we're looking, and then they'll be off again. Or other ones will come in and they'll have been on for a while when we first get on them, and then they disappear while we're looking. So we're not quite sure what to do with these. So they're stars, and they're all Gaia stars. These are all super bright nearby stars, like that one called Z-End. Z-End means it's really bright. It means it has a name, right? It means it has a letter in the constellation it's in. So just in terms of where they are in the HR diagram, so if this is an HR diagram, these are M dwarfs down here, there's sunlight is in here somewhere, and then giant branches up there. And you see they're kind of all over. The only thing they really have in common is that for the most part, they stay away from where most of the other stars are. These are not, so these are all probably young M dwarfs or something like that, some combination of binaries and being young. And these are just some weird evolved stars. But these things, so the mystery of these things is that they are thousands of times more luminous than the brightest solar flares, at least. So thousands to almost 1 million times brighter than the brightest solar flares we see in the millimeter. And most of these are known X-ray emitters. So there's something going on there. So the paper came out recently, which is down there. The other thing that's weird about this is that, so this is the spectral index. So we have two frequencies. We have three frequencies. So this is 95 to 150. This is 150 to 220. So if you're top left, that means that you're falling and then rising between, so 150 to 220 being large means you're going up. So this would be flux versus frequency would be a smile. Here's you're rising and you're rising. Here's you're rising and then falling. And here's you're just falling and falling. So a typical radio source would be down here. And everything that we see for solar, almost all the solar flares have a spectrum that's somewhere down here. If it was some, if we were seeing the peak of some optically thick synchrotron as turning over, it would be down here. There's not much up here, but it's pretty noisy. But what you generally see is that these spectra are gently rising. And the question is, what gives you gently rising emission, mu to the 1 at a millimeter frequencies? So I'm in Illinois. One of the people who's in the office, 2 offices over from me, is Charles Gammy. And what we've discovered is that it's possible that the physical conditions here are actually pretty similar to the physical conditions around Sagittarius star. It's kind of a similar density, and it is true that these Event Horizon Telescope observations are also in this regime where they're looking at things that are optically thick, becoming optically thin in the millimeter. So it's possible that we could do some joint analysis and try to figure out what this stuff is. But right now, it's not really clear what this emission is.
In general, more energetic flares, so higher plasma densities, and that's the rough reason you would expect harder high frequency.
Yeah.
I guess.
Yeah, like if you can get your envelope out and you put everything together and it kind of holds together. But it'd be nice to really understand what this system is. So for one thing, you could look in the optical to see what's going on in the optical. This is going on. If we could get X-ray observations, there's lots of things to do. Yes.
Cool question. Why is there X-axis error bars but not Y?
So basically, there are no error bars on points where the 220 flux is almost unmeasured. So if you don't see a Y error bar, it means the error bar is very large. It's kind of counterintuitive. But it's mainly just there because if we put the error bars on there, they would just be all over the place. So everything down here is effectively an upper limit for the purposes of 220 gigahertz. So it's just saying that it's almost certainly disappeared by the time you get to 220. All right, so those are our various objects. We can also make maps of weak gravitational lensing. So to people that are not CMB, when I say weak gravitational lensing, they're imagining something like this, where I said, so I'm going to say, I put a lens by hand falsely in this image, where is it? And you've been trained, and you'll say, oh, I'm going to look for the spots where the galaxies are tangentially sheared, and I can use that as a way to estimate how much mass is in it, right? So that's the effect of weak gravitational lensing. However, it's also true that if you just look at the separation between objects, so you can see that the characteristic spacing between objects is much larger here than it is out here. And what's that saying? That's saying that the clustering length of the galaxies has been changed. I've changed the 2-point correlations of the galaxies at this location. So not only have I changed like the local shape of individual peaks, I've changed the distance between the peaks. I've changed their clustering. So the CMB version of this is very similar. That you look at this and you say, oh, there's actually some spot where the CMB's 2-point, the clustering of the CMB, the shapes of these things, the separations between them, has a different structure here versus here versus here. I've made the 2-point correlation function anisotropic. There's different spots. I've broken statistical isotropy. This spot is different from this spot, but it's only different in its statistics. So that's CMB lensing, and so you can basically construct an estimator which will go look for spots where this has happened. And I'm sure there have been many people coming through CITA talking about this. So many people have done this. So this is what we're doing in SPT, and so we're actually not ready to publish what we've got yet, so we're still working on some internal projects. But just to give you, this is just marketing for what's coming. There's a simulation of signal plus noise. That's just the noise. So you look at this and you say, oh, there's a lot more structure up here than down here. It tells you that we are going to be measuring lots of signal. So what does that mean? Well, so this is, since none of you can do spherical harmonic transforms in your head, this is our map. This is a map of gravitational lensing in the SPT patch. So this was generated by Cale Daly, who's my student at Illinois, but Yuki Amori is also doing a lot of this at Chicago, and Mary Smollett is doing a Bayesian version, which is quite beautiful. So to put it in perspective, if you just want to say, what would it look like if you started with the Planck map? So this is the Wiener filter Planck map in that same patch, and we're just going to weave in the SPT one. And you see that we're adding a lot more information just by folding in that SPT map. So this is SPT plus Planck, that's Planck. And what you can see is, you see a lot of, well, if we did this, you can see the structures that survive and just really come into focus. And then we can do this to do, obviously take power spectrum. But we're not ready to publish this. This is probably going to be a while before this particular map comes out. But it's coming certainly in this year. All right, now, the other thing we can talk about is mapping the velocity field. And so this involves the idea of the kinetic Snezl-Dobich effect. So I think the best view of this is a cartoon by Matt Matabashirul, that's been buried down here again. I swear that all of the credit for all this stuff is down here. I've been very generous in my citations, and it's all for naught. So let's imagine that you have some cosmic velocity mode where this is the line of sight velocity. So this is the line of sight velocity. If you were to make a CMB map of that location, what you would see is you would see in the background CMB, and then where you have a lot of large scale structure that's all moving away from you, everything would appear cold. So you get cold spots at the location of every galaxy because it's all moving away from you along the line of sight. Where there's no movement, then you get no Compton scattering. So, well, you get the Compton scattering, but there's no V over C, so you get see no signal there, see not much of a signal there. Where everything's moving towards you, you see little hot spots because you have all these galaxies moving towards you. These moving mirrors are doing some upscattering. And so one thing you could look for is you can look for a cross correlation between your galaxies and this small scale structure, and you could use that as an estimate of this velocity. If I cross correlate, if I basically compare this map with this map, I could reconstruct this. That's one thing you could do. The other thing you could do is you could actually say, well, if I was to only look at the small scale structure in this map, so if I just did a power spectrum of just of high L, and say how much RMS is there in little tiny cells, what I would find is that there's lots of power here, and there's lots of power here, and there's no power here. So my high L power spectrum will have large scale variations from place to place. So this spot's got a lot of power, this spot has 0 power, this has lots of power. And I've thrown away the phase here, but it's still true that if I do my CLs, I'll get different answers in different spots. And how that's different will depend on how my galaxies are, the amount of power I have depends on the galaxy distribution here, which is to say where are all my electrons and how are they moving. So just this version of seeing small scale structure that is related to where the things are moving and where the galaxies are has been detected a bunch of times. So ACT has done it, Planck has done it, SPT has done it, and that's by doing a cross correlation where you use galaxies as a tracer of V and galaxies as a tracer of the little dots, and then comparing that with your CMB map. You make a template for this using an estimate of the velocity, an estimate of the galaxy density, and make an estimate for these small scale templates, and then do a cross correlation. So that's a GGT bispectrum, and that's been done many times now by multiple experiments. And that tells you something about the relationship between galaxies and electrons. So that's been done. The other thing you could do is you could say, well, galaxies are fun, but we kind of know a lot about galaxies already. But something that people don't know very much about is reionization. And so in reionization, instead of them being all these little dots, instead you'd have these big bubbles that are all either moving towards you or away from you, modulated by the velocity field. And so what that's saying is that you should get these very large scale fluctuations in this KSZ power. So I modulate this by the velocity field, and I'll see lots of power on the scale of the bubbles here, lots of power on the scale of the bubbles here, no power in here, and I can use that as some estimator for how much power is coming from reionization. So we could do this to search for what's going on in reionization. And so if you say, what is the optimal estimator for this? It's actually surprising if you construct this optimal estimator. The optimal estimator, it just says you filter out the CMB. So you take the large scale fluctuations and you just filter it out. Filter out your noise on small scales, and you literally just square your map. So you do a filtered map, you square it, and then take the angular power spectrum of the square of your map. So that's a 4-point function, right? Because you square the map, and then you're doing a power spectrum of it. So that is 4 units of microkelvin in it, 4 powers of microkelvin. And then you just look at that angular power spectrum, and you see what you see. And so we tried that. And so what did we use to try that with? Well, so this is Srini Raghunathan, who is a postdoc at NCSA, which is in Illinois. So it's a terrifying exercise because squaring your map is terrifying. You have all sorts of things. Your foregrounds have all sorts of non-Gaussianity. And so here's what we found for, first of all, we use these SPT, what we call them mega deep. We have 100 square degrees. It was imaged by SPT pole twice. And SPT 3G, and this is only the first 2 years of that. We threw in some Herschel data, so it's only 100 square degrees. It's pretty deep in its map depth. So it's actually not quite at SPT 3G depth, but it's pretty deep. And then we looked at the reionization prediction. So let's just go through what this plot means. Okay, so the green is what we see with SPT. This is take the square of the map, take the angular power spectrum of it, and you see that it's kind of rising. This blue line has already been subtracted out of the data because this is what you would get if you just did the same operation on a Gaussian field. That's what we call M0 or whatever you want to call it. So a Gaussian, just from the power that we know is in the maps, we get this blue line, so we subtracted that out. And then this black line is what we think would be the non-Gaussian 4-point from the foregrounds. And now this is the scary thing because the foregrounds are SD in the cosmic infrared background, and we don't really know those very well. And what you see is that those are awfully similar to our points. So what we think is we've detected the non-Gaussian 4-point from foregrounds, and the level that we expect the non-Gaussian KSZ from SIMS is this sort of, I don't even know what to call it, it's peach down here. This is the signal we're looking for as we ramp through a variety of reionization histories. And so what we have is we have an upper limit on the presence of any kind of large non-Gaussian entity from KSZ. And so it's a little bit scary because this, these are far and away the deepest CMB maps that are in existence, and it's still hard. So we'll see what we do next, but let's see what we get to. So you can turn this into limits on reionization. And so this is if you parameterize it as the midpoint of reionization when it was at 50%. And the duration, I think this is delta Z 50, so 50% on either side. So this is duration, this is how long reionization took, this is when it happened. And now you read these numbers off, you see, okay, this would say, did reionization happen at redshift 15? And did it take a long time? Is out here. And the answer is no. Reionization did not happen at redshift 15 and happened very slowly. So everything up here is excluded. Now, just from Planck, if you say, what's the Planck tau? Planck tau already said that reionization couldn't have happened before redshift 10, or there'd be too much optical depth. So this is the way you would expect from Planck. If instead you were to go talk to an astronomer, and an astronomer would say, well, we know that reionization was done by a redshift of 6, because we don't see a Gunn-Peterson trough at low Z. So the astronomers would say that we already knew we lived somewhere like this. So Planck would say we live somewhere like this. And so what it says is that this 4-point function is not denting the consensus of what was going on for reionization, which is it must have happened somewhere around a redshift of 6, 8, and it had to have happened pretty quickly. And that's just saying what's the Planck optical depth and do we see a Gunn-Peterson trough at redshift of 5? And so that's kind of pinches you off into this space down here. So we're not down to there yet in terms of our constraint from KSZ. However, what if our interpretation of Planck is wrong? So that's, if we know that our quadrupole is low at redshift 0, what if it's always low? There's some symmetry of the universe we don't understand, like Craig Hogan says. Maybe there's something we don't understand. Maybe everyone measures a low quadrupole, in which case Planck would give you no constraint on reionization. This tells us that reionization had to have happened at reasonably low redshift and had to have happened reasonably quickly. So we're getting there, and so as we get better at doing these analyses, we'll be able to squeeze into this. Hopefully we can start squeezing into here a little bit and actually start putting some direction. What we want to do is do a measurement right there. That's our plan. There's a measurement right there. We'll see how it goes. All right. So that's it. So CMB surveys, we're doing deep millimeter wave surveys. So we're not just measuring cosmological parameters and searching for non-Gaussianity or gravity waves from inflation. We're doing all those things, but there's also lots of room for new things to do in astrophysics. We can see sources that can't be seen in other ways. We're opening up the time-varying millimeter wave sky. Like, we have these daily maps over thousands of square degrees. So far, we're really just seeing flares are the only new thing we've seen so far, and AGN flickering, a bunch of AGN. AGN are flickering all the time. We have this AGN monitoring, we can do that. We have these moving objects. What we were hoping to find were some GRBs and some orphan afterglows. It doesn't seem like there are a lot of orphan afterglows, so we haven't actually found any interesting extragalactic transients yet. And now we're on 5 years of looking, so we'll see where that goes. We also have these lensing maps. So these lensing maps are actually, if you just say per pixel, these are basically at least as deep as the deepest cosmic shear maps. You just say, what is the noise per pixel in this weak lensing map? These are the highest signal noise per pixel maps that you'll see that aren't done with, say, HST or something like that. And then where we are is searching for reionization. These measurements, what we've learned is that they're really hard. But reionization didn't happen super early. And that is independent from what anyone else, what else we know about reionization. All right, so I'll leave it there and answer questions.
Do we have any additional questions in the room?
Could you explain that degeneracy in the last quote?
So this degeneracy this is a line of constant 4-point functions. So what's going on is that if reionization happened for a long time, and that means you just got a lot of bubbles along the line of sight, and all those bubbles are jostling back and forth, and that just gives you a large amount of RMS fluctuation. So it's basically just saying how many bubbles are you getting per square degree. So you get lots of bubbles down here if reionization went for a long time, they all get superimposed. Up here, the optical depth is really high, so each bubble has a lot of electrons, just because at high redshift everything's more dense. So here, each bubble is quite powerful, but you don't have very many of them.
Big dick is hand up.
Sure. Yeah, Dick. What are you?
Yeah, hi, Gil. I'll see you in a couple of minutes, but I had to zoom in from a distance here. I completely agree with you, in spite being a card-carrying Planckian, that many things could happen to modified tau, and there are reasons to think that something at such low L does occur in the universe. And so we have our own ways of fooling around with this. But maybe you can amplify a bit on the mysterious comment about my good friend Craig Hogan. And I actually think Nate's an expert on this. But
yeah, that's what I was thinking. I think Nate is the expert on.
Yeah, but I want your take on it.
Okay, so I can't say I've read Craig's paper in great detail.
Nor am I, I'm afraid.
Craig Hogan has a paper that is basically speculating that there effectively are no acausal correlations beyond the horizon. That if there's some symmetry that just requires that you cannot have a correlation function that has power beyond the scale of the local horizon, then that would explain why the cosmic microwave background seems to show no fluctuations on scales above, I don't know, 60, 80, 90 degrees, whatever the number is.
75.
75, good. So above 75 degrees, there's CMB 2-point correlation function is oddly consistent with 0. Like you look at it and you say, boy, that sure looks like 0. And then you look at what it's supposed to look like and you'd say, well, I don't know. Now, I think it seems like it is consistent with cosmic variance. It's just when you run any sim, none of those sims look that close to 0, and 0 is kind of a funny number. With that being said, like, he doesn't really have a reason why that must be true. It just says, well, if there is some principle if there is some symmetry that makes this true, then this is what you would expect. And so that would be interesting if something similar is going on in the scale of, if that was the reason why our quadrupole was low, that would totally mess up all measurements of tau.
Yeah, just my take on all this is that there should be no dogmatism in our subjects. So you got to be able to probe these things with impunity, and many things could happen at the very low L's. Anyway, so it's interesting, and I agree that what will happen eventually is that as we get more and more information about reionization, you might even be able to close the door on some of those extreme models.
Yeah, and I guess the optimistic view of this is that we could actually use this to eventually do a measurement of the RMS quadrupole power at reionization.
Yeah, although I completely agree with you, 4.8 easy.
Yeah.
Anyway, we'll be chatting about this more over dinner and other things. I'll see you in the not too distant future.
Yeah, and just to be clear, like 4-point, Srini has been working forever on 2-point, and then we were told by lots of people that 4-point was way easier. And 4-point's not easy. But there is an argument that Kendrick Smith makes that 4-point is actually easier than 2-point. And I think that what Srini has learned is that that's not necessarily true.
Yeah, I think Srini's on to something there, because you're basically just stretching out the Gaussian a bit in order to make it 4 compatible with 4. Anyway, this will be fun. Great talk, and right across the board, everybody is excited about these variable sources. Just had a big discussion today about it. Anyway, so look forward to chatting with you more about it.
All right, great.
Okay, do we have any other questions online or in the room? If not, I think we can adjourn, and there should be some tea and coffee and cookies upstairs.
All right.
Thanks again.